Hi guys, can I get a voice check, sound check?
Quack.
Okay.
I but not very well.
What's that, guys? You guys are. I'm probably breaking up. You guys sound like you're breaking up.
Oh, he was breaking up for me too, so I don't think it's you.
Okay.
Yeah, same here.
Okay. Thanks, guys. Um, let's see. How are we doing? Okay.
I don't like daylight savings.
Sorry.
I don't like daylight savings.
Oh yeah.
No,
Why is that? I'm kind of.
because I have to get up an hour earlier.
Oh, I see. Well, but it's like light outside now. That's kind of cool. But I guess it's dark when you wake. I don't know. Yeah, my wife wakes me up super early, so I don't know. The nice thing is it's the first sign that we're like exiting the winter. I always find that encouraging. Meetings start. All right. Okay, guys, we can get started. So the first thing I was going to do is just quickly go over the quiz 2 solutions. So let's see, the problem looked like this. We had a diode and a couple of resistors, and then a battery. Hope that looks right. And the out. And this was, the battery was 2 volts and 1K, 1K. I forgot, I guess this was probably R1. This was probably R2. So the first question was transfer function with ideal diode. And I think we did this a bunch of times. It's kind of like the same procedure. Sometimes it gets a little confusing, but it's kind of the same number of steps. So first you look at Vn being really low. So if Vn is low, the anode is below the cathode. So the diode is off. So I'll just replace it with an open switch. So here, if this guy is open, right? So this guy's open, there's no current flowing anywhere. So there's no voltage drop across, say, this resistor, for example, because there's no current flowing. So basically, V out is just going to equal to by KVL, V out is just going to look like VB. So here, V out is just equal to VB. Okay, is equal to 2 volts. Okay, so next, if I look at Vn being very positive, then this guy turns on because this end is higher than this end. And plug that in. That's Vn. So I guess there's a few ways to do this, but I guess how I do it is I just calculate like the current I sub x, which is going to be I sub x is going to be V in minus VB, because it's sort of flowing through here. So this is the KVL. So Vn minus VB over 1 k ohm plus 1 k ohm. Okay, those two resistors. Okay, and then once we have the current, then the output voltage we can get in terms of that current. You can either go from the Vn or Vb. I'll just do it from the Vn. So V out is Vb plus the voltage drop across that guy, which is I sub x times 1 k ohm. Okay, so it's equal to 2 volts plus V in minus 2 volts over 2 k ohm times 1 k ohm. Okay, is 2 volts plus 1/2 V in minus 1/2 of 2 volts. So that's 1 volt. So it's 1/2 V in plus 1 volt. Okay, and then the crossover point is when we set these two guys, we set this and this, these two lines have to intersect, so we set them equal to each other. So V out is equal to 2 volts is equal to 1/2 V in plus 1 volt. So V out, you already have it here for the sort of the crossover point. And then 1/2 V in plus 1 volt is equal to 2 volts. I'm just rewriting this guy because these guys have to intersect. So half V in is 1 volt, so V in is 2 volts. Okay, so that's the intercept point. So if I was going to draw this, now I think some of you guys went wrong here, which is that when V out is, you got V in, V out is equal to 2 volts below the crossover point, but then you gave it a slope. So I think you just got to have to trust the math a little bit. I mean, you need to have both a feel for this stuff and to trust the math. So if the math says below this point, V out is just equal to 2 volts, it's just, below, so we go, this is 2 volts, which is this is V in, this is V out. So V in and V out is the crossover point, so that's where we have this point here. So anything less than this, V out is just equal to 2 volts. So it's going to be, a straight line going through, it should be 2 volts. Through 2 volts. It's not going to have some weird slope or something. It's just 2 volts. It's not a function of V in at all. So it's a straight line. And then after that, we can just sort of ignore this guy because we're just looking at the slope. V out is just equal to half of V in. So V out would be like something like that, with the slope being 1/2. Okay, any questions about that first part?
Professor?
Yeah,
Oh, Professor. Did you use I'm sorry. For the V out on the right side, did you use like did you just solve for that node? So V out right there. Is that just like, do you just use like any kind of analysis here? Like,
here to do this.
yeah,
Yeah, so I guess this
yeah,
is
to get that.
part of the sorry, it's part of the confusion, I guess. Sometimes. So when you look at V out here, I forgot how you always have to remember it's like if this is drawn as a ground, it's with reference to ground, or it's with reference to this guy. So you could look at it as a KVL starting from here. So starting from ground, going through VB, going through V, whatever is the voltage across this resistor, minus V out is equal to 0. So that's one way to look at it. So this is kind of what so if I was going to write that as a KVL, it would be VB minus IX. Sorry, hold on a second. No, I guess the current's going this way. So it'd be plus IX, oops, plus IX 1K ohm minus V out is equal to 0. And then write it as V out is equal to VB plus IX 1K ohm. So I'm doing sort of 2K, I'm doing 2 KVLs here. So one is Vn minus IX 1K ohm minus IX 1K ohm minus VB is equal to 0. And I didn't really write that, but that was the equation. And then I sort of move it around and I get IX is equal to this. Did that make sense, Nelson? That first KVL?
I think so.
I can write it for you. So that first KVL would be around this branch. Do you see how this is like, I know it can be confusing that this is ground. So although
Yeah, so those are connected, right? Yeah.
they're connected. So if I was going to draw it as KVL, I would do Vn minus IX 1K ohm minus IX 1K ohm. So that would be one resistance, two resistance, minus V.
Oh, I see. Okay. Right.
Yeah, so I'm doing a shortcut here, but it's a KVL essentially. And then the second, so that's just to get I sub X so that I can figure out what's the voltage drop across here, because I know the next thing I want to do is a KVL here, which would be this guy minus the voltage drop across this, but I don't know what that is, so I need to somehow put it in terms of I sub X. Does that help?
Yeah, that makes sense.
Yeah. Sorry, I guess I'm still kind of taking shortcuts here, but it's probably a bad idea. So, but anyway, 2 KVLs basically. What did you see that, or you didn't see that in the quiz?
Oh no, I just assumed that that we only used Vn and Vb, because I remember hearing something about how, like, the resistor doesn't really matter or something. I don't know. So I completely ignored the resistor in that part when I did the KVL. So I guess that was my mistake.
So you thought that, so Vn minus Vb kind of a thing.
Yeah, that's what I thought. I thought it was just Vn minus Vb.
Got it. I mean, it's only true if there is no current flowing. But because you have a voltage here that's different than the voltage, or it could be different than the voltage here, as soon as those two voltages are different, then you'll have a current flowing. And you'll have
Got it. Okay, that makes sense.
resistors. Yeah, the only time you won't have a current flowing is when Vn is equal to 2 volts, so that, we won't get a current flow. So, and I guess that's why, yeah, that makes sense. As when Vn is equal to exactly 2 volts, you don't get any current flowing. So V out is just VB, which is this point here. Is another way to look at it. Hmm. Yeah, I don't, so I'm not sure what advice to give in terms of figuring out, doing the KVL and KCL thing, except just, lots of practice, I guess. But, and then just kind of like, lots of practice, try to be systematic. Yeah, I think Melvin's right. I think you could think about doing a voltage divider. But, sometimes I think the voltage divider does, well, it depends on how good you are with the voltage divider. Sometimes it can steer you wrong. I mean, that's the other thing is you could just imagine you do a voltage divider here and add VB, but it doesn't always end up giving you the right answer, at least in my experience. So it just depends on, but I just get lots of practice on KCL and KVL, and we'll be continuing to do KVL and KCL, and it's going to get sort of a little bit more involved, as a matter of fact, with the bipolar transistors, I think, because now you got 3 terminals and sort of more complicated, sort of slightly more complicated circuits. So just get comfortable with it. Okay, so let's do the same thing, except now we do the same. It was the same circuit, but we do the just redraw it because my brain doesn't work. So we want to basically do the same thing, but we wanted it for a constant voltage. Got it. Okay. So again, Vn at minus infinity. So this is going to look like an open circuit, but there's the diodes VD on, but because this side of VD on is open, you're not really going to see the VD on. But I drew it there anyway. So again, if you look at this is floating, right? So there's no current flowing anywhere. So V out is just kind of, again, equal to VB because there's no voltage drop across this resistor because there's no current flowing. So to say V out is equal to VB is equal to 2 volts. So this is somewhere that I'm not sure some of you guys went wrong here. You had quite a few of you guys had this V out being 2.8 volts. So somehow, I'm not sure what your thoughts were, but I noticed that a few times. But again, there's no current flowing, so this V out is just even equal to VB because there's no voltage drop here if you do a KCL. Okay, so then Vn goes to positive infinity, and then we get Vn. Now we get the VD on. VB is equal to 2 volts. Okay, so we do the KCL, sorry, KVL again to get I sub x. So this time, I sub x is Vn minus, now we have this VD on voltage from the diode in the path, minus VB over 1K ohm plus 1K ohm. I guess this ends up being, so this was, in our problem, this was 0.8 volts, and this was 2 volts. So these two are minus 2.8 volts. Okay, and then V out, we again do KVL from, or that's what I do from here to here. And I ended up with VB plus I sub x times 1K ohm. So 2 volts plus V in minus 2.8 volts over 2K ohm times 1K ohm. So that's equal to, so V out is 1/2 V in, and then plus 2 volts minus, so it's 1/2 of 2.8 is 1.4 volts, right? So it's equal to 1/2 V in plus 0.6 volts. Okay. So when we do the crossover, so V out is VB is 2 volts is equal to, just at the crossover point, these two equal to each other. Vn plus 0.6 volts. Okay, so first thing is we have the V out value, so it's 2 volts. And then we have 2 volts is equal to 1/2 Vn plus 0.6 volts. So half Vn is 1.4 volts and Vn is 2.8 volts. Okay, so our crossover point just moved to 2.8 volts for Vn, but the V out crossover point stayed at 2 volts. Okay, and everywhere below, V out is 2 volts, and everywhere above, V out is, 1/2 slope of 1/2 Vn. Any questions about that?
Need time.
Sorry? Arthur, did you have a question?
No, I just need time to write down notes.
Oh, sure, sorry. And you had the question about the minus 2.8 volts, so this is minus 0.8 and a minus 2, so they're just I'm just doing the math. Arthur, let me know when you're done, or anybody else if you guys want me to hold off.
Okay. I got it.
So what I want to say about this. So this is like, I think in the first lecture, and it says it in the book, in the sort of the introductory section of the book, is advice to students. Guys, might be a good time to go back and look at advice to students from the author, who, again, I think really is a great teacher. So he was saying, this class or microelectronics, this type of analysis really needs two things to work together. One of them is you have to, and both of them, really honestly, both of them you get by doing lots of problems and lots of designs. And what, half of the game is the math and trying to do the math systematically. As you guys can see, I'm not 100% doing it systematically. I'm jumping over some steps. It shouldn't be, but just sort of like, second nature. So systematically do the math and trust the math. And then the second half of the game is develop an intuition about what the circuits are going to do. And the only way to do that is just do lots of problems. So lots and lots of homework problems, just to get you familiar with it. I don't know if there's any other way. I used to make the mistake in, I think if it was the biggest mistake I made in undergrad was I would just sort of like read the book, and that was my primary thing. So, I may go to the lecture, maybe not. Nobody really cared. We had like these huge classes. And then I wouldn't do a lot of problems unless it was like a graded homework or something. But I should have really flipped that around, which is do check out the lectures, because what I try to do, maybe not successfully, but I try to do is to focus on the important points that we're going to cover, and then do a lot of homework problems, or do a lot of sample problems. And then lastly, if you have to, go and look at the book, okay, just to help you solve the problems. So that's, again, just my advice, and I think the author's dead bang on in terms of the only way to do it is to just do it over and over again to get some kind of intuition. And that's all. Intuition is all relative. I mean, like after years and years of doing this, I have intuition about circuits that I've done a lot, and I don't have a lot of intuition about other circuits, and I just have to kind of like really analyze the hell out of them, look at them in a bunch of different ways. Anyhow, so the last problem was, a voltage against time transfer function, and it said, if this input voltage, then it was the ideal diode case. Okay, so this the input voltage, if that was so Vn is V0, I don't know if it was cos or sine, this doesn't matter. Sine of omega t, with V0 being 5 volts, what would the output look like as a function of time? Okay, so one thing that I think a lot of people got wrong is just what does this look like? Okay, a bunch of people thought that this was like somehow centered around 5 volts or something like that. But that's not what V0 sine of omega t looks like. That would be if I had a offset plus V0 sine of omega t, and V0 was something else. But so without this, offset, so what's given in the problem is you just take the sine function, which goes from 1 to -1, and you multiply it by V0. So it's basically a sine wave centered around 0 that goes up and down from V0 to -V0. That's like a really poor looking sine wave. But that's kind of the first thing, is what the input looks like. Okay. So again, you gotta like trust the math when you see something like this equation. got to know that there's no offset, and it's just basically is calling out the, it's multiplying this amplitude by this sine. And, it's as simple as that. Sine goes from -1 to 1, and V0 multiplies by two zeros at the zero crossings, and V0 at the.
Professor,
Yeah.
is it VO cosine? Is that sine? Or is it just me?
I'm sorry?
Is it cosine of that sine?
Oh, it
Or
might be the
just prob-
cosine. Yeah, maybe I'm writing it wrong. But it's, the idea is like, because it's like, where is this time zero? Could be here. Like, there's kind of like no definition of time zero or negative time. So it's really kind of sine and cosine to me are like kind of the same thing. It's just people call it a sine wave because there's no such concept of time zero, if that makes sense. So you could take, if you take a cosine or a sine, they're basically like sort of 90-degree out of phase with each other, right? 90-degree out of phase, yeah. Does that make sense? Am I confusing you guys?
Professor?
Yeah.
So this is pretty much it. Like it's just that V out like that, and then negative V out, and then just. So what about the 5 volts then?
Yeah. So
Oh no, that's just 5. Yeah. Okay.
this is just the input now. Now we got to stick this input into something that has a transfer function like, so this is Vn. Okay, so that's going to get stuck into something that has a transfer function like, 2 volt and 2 volt. So if I was going to draw this guy, sort of like the suggesting that this is like a really sort of a, it's not a scientific method, but you just sort of like try to plot that on this and look at what happens. So if I was going to draw the V out, so this is 5 volts. So if this was Vn. So if I was going to draw V out, anytime Vn is less than 2 volts, right? Then V out is 2 volts. So anytime Vn, let's say that's 2 volts. Anytime Vn is less than 2 volts, V out is just stuck at 2 volts. So if I was going to draw it, let me draw it with red. Whoops. So this is 2 volts. So Vn here is less than 2 volts. So V out is just going to be red. So like all along here, notice Vn is less than 2 volts. So V out is just stuck at 2 volts. Okay. And anytime V out is higher than 2 volts, sorry, Vn is higher than 2 volts, then in that case, V out, remember this is 1/2 slope. So anywhere above this, V out is going to be 1/2 Vn. So it's going to be like lower version of that. Okay, and specifically the equation is going to look like this for the ideal diode. So V out is 1/2 Vn plus 1. So plus 1. V out is 1/2 Vn plus 1 volt. Just clean that up, sorry guys. So I can do like maybe just looking at it at this point. Oops. Looking at it here, Vn is 5 volts. So if I just look at what the V out would look like here at its peak, 1/2 of 5 volts plus 1 volt. So it would be 2.5 volts plus 1 volt is 3.5 volts. So it would basically be 3.5 volts at its peak. So that's what V out would look like. Okay, any questions about that, guys?
Professor.
Yeah.
So I noticed there's that sine wave that's going down.
This guy?
How exactly does that? Yeah, how does that work exactly?
Boy, that's kind of like, it's confusing. It's something that the book does. It's like I guess I'd call it a visualization tool. It's not anything scientific. It's sort of superimposing two graphs, right? So one is the graph of, so this part above here is the graph of V in minus V out. Okay, so on top, right? And below here, it's really a whole other graph. It's time versus Vn. So they share this axis. This graph and this graph share this axis, which is Vn.
Oh, so this is just a separate graph then. Like if you tilt your head to the side, then that's kind of like.
Yeah, it's like a visualization tool to see, hey, if I multiply this by this transfer function, it's supposed to help you sort of like figure that out. So if I like, now you can see how like here Vn, like this section is all V out is 2 volts, and this area V out is all 1/2. Does that make sense? It's sort of a visualization method that the books are.
Yeah. Yeah, that makes sense.
Otherwise, you can really do the same thing. I mean, it's just, you don't really need to do that. You just need to sort of keep track of the fact that you have this transfer function with this input. And anytime this, I mean, this kind of tells you, right? Anytime Vn is less than 2 volts, V out is just 2 volts. So V out would be anytime Vn is like, anytime it's less than 2 volts, V out is just pegged at 2 volts. And anytime Vn is larger than 2 volts, V out is 1/2 of Vn. So it would just be 1/2 of, so Vn would be this, and V out would be something smaller. And we calculated, this peak point was just 3.5 volts. And like I would say like a bunch of people, I gave you guys full credit, even if you had something that looked like kind of semi like this. I think just a few people actually got it right. Maybe like really like 2 people. But I was just, I wasn't being too harsh on grading this one. Okay, any other questions, guys? Okay, so good news, bad news. Good news is we're kind of like done with the core of the diode stuff, although like it's immediately going to show up again in different guise. Sort of in part of the bipolar transistor thinking. So that's the good news, is like we're off to the next step. Sorry guys, my dog is going nuts. Are you here? Do you guys hear my dog? I'm hoping this microphone.
Or like
Yeah.
Yeah.
about 30 minutes.
Sorry guys. Well, what should I do?
It's not that bad. It's fine.
Let's give her one more chance. Otherwise, I'm gonna have to go close. She's just barking at people walking outside with their dogs, so I just have to go close the drapes. But this is all the fun she gets. So anyway, but if she starts again, I'll go and close the drapes. Anyway, so that was the bipolar. We're moving to the bipolar. So the diode, in some ways, you can sort of start focusing on this bipolar now. Now the bad news is that all the same techniques we're gonna, it's all KVLs, KCLs, and those kind of things. So, but it's just maybe sort of like a fresh look. Anyway, so we talked last time about how if you had a voltage dependent current source, if you had such a device, you could put a resistor here and get an amplifier out of this. And the idea behind an amplifier is that when you look at the ratio between the output and the input, is you get some kind of a gain. There's an increase in amplitude on the output compared to the input. Now, one of the things that's a little bit confusing about this early on is a lot of times this is a negative gain. Negative gain doesn't mean attenuation. It just means the sign of the output is inverted with respect to the input. It's just the way circuits usually work out. Typically you end up getting negative gain, but in most cases it doesn't matter, as we'll see. And in fact, in most cases, we probably won't get too much into this in this class. I don't think we'll have time, but in most cases, you're gonna use the amp. I don't want to confuse you guys. We're not gonna get into this, but just you'll hear this all your whole life as electrical engineers, is you want negative feedback, okay? And basically negative feedback is this really beautiful method of making everything really linear and controllable. It's great. It's just, I can't tell you how powerful of that thought, a concept, I don't know who came up with it, is this negative feedback. It's very like counterintuitive. Why do you want negative feedback? Why do you want something to be negative? It's just a way of really controlling things. But anyhow, so the fact that you have a negative amplifier, output amplifier, actually like really helps you, because you're going to use sort of this negative version of the output is what you'd really like to somehow, through a network of other circuit components, bring it back to the input and linearize things and control things, etc. But anyway, it's something that's slightly confusing, but don't let it confuse you guys. It's not this negative gain. It's not attenuation. It's just a sign. So, if the in is going, is high going, the V out is low going. But in either case, V out is a bigger version of V in the voltage domain. Gain can be 95% of the time. What you guys will encounter is voltage output to voltage input gain, but you can really be kind of and amplifiers can be implemented any combination of voltage and current. So current input, voltage output, whatever, voltage input, current output. But again, most of the time you're going to see voltage in, voltage out. Okay, and certainly in this class. Okay, so basically this is the circuit. Forget about this Rn for now. I'm not going to get into that, but okay. So that's, if the main idea is, if we had such a beast and an external resistor, we would get a gain, which would be the external resistor value times this K value. That's the transfer function of this voltage dependent current source. Do you guys want me to explain this in detail, or was it like, was it pretty clear? We're gonna sort of hit this over and over again. Anyway, speak up if you want me to like step through this again, but we'll see it again. Anybody going once, going twice?
Professor, I have a quick question.
Yeah, it's okay.
Why isn't the wires for U1 directly connected to the voltage dependent current source? Like, you see where it's floating.
Yeah, so imagine if you input, that would be like real trouble, because if you connected this voltage source straight to here, and you have like a V in and the current, you would have like a real weird situation, because this would actually Now notice something. Now, doesn't matter what happens here. This V out is just shorted to V in this case. So V out in this case would always be equal to V in. Okay, so this, and then you'd end up getting this current, which would be, you know, like this current could get V in or equal to V out divided by, you know, whatever this R sub L is here. You get some current going through here, which would be just that. And then you'd have this current just going through here. So it wouldn't, like, if you think about it, it wouldn't do anything. It would just sort of be V out would just equal to V in. Again, because you'd be just shorting V out to V in. Okay, so the way to look at this is that it is a, so let me move this down. And I gotta admit, I'm trying to remember what it was like seeing this stuff for the first time. So it is confusing. But the way to look at this is now it's not a 2-terminal device. We have a 3-terminal device. Okay, what are the 3 terminals? Okay, so there's one is this terminal here. Okay, 2 is this terminal here, which is V out. And then we normally connect these 2. Now would be our 3rd terminal. So this guy isn't going to be necessarily connected to this point. In fact, you don't want it to be. Well, I guess it could be connected. In some circuits, they are connected, but it wouldn't give you a gain from input to output.
So you're just drawing what the BJT would look like, roughly?
Sure. If you do if I draw this as a BJT, okay, so the emitter would be here. This is the emitter. So I'm just jumping ahead because Kevin asked me to, but we're going to come back and do this just in a few slides. So the base would be here. Okay, and the collector is here. So if you were going to set this up as a gain circuit, you would put your V in here, and you would put, you know, resistor here. Okay, so this guy would not be connected to here. Now, it is permissible, and sometimes you do it, is you have a situation where you have the base connected to the collector, which is kind of the situation you're describing, or you were wondering about, which was this connected to this. And that's used in like a different circuit, and it's like a current mirror, but I don't want to confuse the discussion. But it's used, but it won't give you a gain if you say this is the input and this is the output. I don't know, I'll put a ground here and put a resistor here, whatever I do. It's not going to give me a gain, a voltage gain from output to input. So it is a permissible connection that you could have in a circuit, but it won't give you a gain function. It'll give you some other function.
Okay, thank you.
Sure. Okay, so that was that. So if we had such a thing, we get it. And in fact, what we have is a bipolar transistor. So, which, you know, we'll jump to here, but this is what it'll look like, the bipolar transistor. It's a 3-terminal device. It has an input, an output, and so there's this reference terminal, let's say, okay? And again, I'm like, it's really a more general type of thing, but I don't want to make it like everything's permissible at this point. Let's just sort of focus on the first way to hook this up, and then we'll see that in fact you can sort of, like Kevin was asking, we can hook it up in different ways. But when you want to hook it up as a gain element, to first, as a first thing is you just see this as a reference point, this as an input, this is an output. And if I put a resistor here, this would, and then K would be basically sort of this function. Now notice that this isn't K, we had K here, and it looked like a constant. And fortunately, unfortunately, I think it's more fortunately, that function from voltage in to current out is actually an exponential function. So it kind of looks like our diode, and you guys will see why. So basically, your I here looks like I sub s exponential of this V1 over VT, and that VT, this again looks like our diode VD I sub D. I drew this really a little too like this. So out here, if you guys remember, the I sub D was I sub s exponential of VD over VT. Okay, so then that's what it really looks like. So it's not a constant, but it's the same exponential function we get in a diode. This relationship between this current coming out into this terminal 3, or getting pulled from this terminal 3, or getting sunk into the transistor. Remember, you got to remember that the current's going in. And the function as a function of V1 is this exponential function. And then VT is our old, 26 millivolts, or KT over Q, 26 millivolts at room temperature. Okay. Okay, so this is sort of the like I said, the bad news, the diode's going to keep coming back, because in some ways bipolar transistors are made from two diodes that are intimately linked to each other. And that's why we covered the diode first, so that it wouldn't be the first time you saw it here when things get confusing. So this is what a bipolar transistor looks like. Okay, so basically the idea is, I'm going to sort of draw it this way. So you have one diode, this looks like a diode, right? So this is an NP diode. So if I was going to draw it as a diode, it would look like this, right? And then the idea is that I can actually stick another N on this side. And this PN is also going to be another diode that's going to be facing the other way. And they're kind of connected here, this connectivity here. So this is where you get your three terminals. You get one connection here, one connection here, one connection here. Okay. And we're going to go through this in detail. And so drawn, flipped 90 degrees, you get this guy. So this is one PN junction, and here's the other PN junction. Now, this one of the secrets, and again, I'm sorry, I keep jumping ahead, but I want you guys to know this ahead of time, is the reason this acts as in a very special way, it doesn't really act like two back-to-back diodes, because you make this P so thin that this junction interacts with this junction. So it's not just two back-to-back diodes. I just drew it there to have you guys sort of see the relationship with the diode. But in fact, this junction and this junction are intimately related, and you'll see how. And that's the way the transistor works. It's the magic of how the transistor works. But again, if we just kind of draw this as this NPN, as it's called. So this is called a bipolar transistor. it's called this is called an NPN. You could also have a bipolar transistor that has two diodes and looks like this. This would be called a PNP, which looks, acts in a slightly different, and not, it acts like in a flipped version compared to NPN. We're going to get to this later. So right now, let's look at this bipolar transistor here. So it's got the three terminals. It's got the collector, base, and emitter. Okay, remember now that our diode was just, I don't know, NP, and was just two terminals that had the anode and the cathode. Now we're looking at three terminals. Okay, and here's the circuit symbol for the bipolar transistor. Same thing, it just looks different. And so the arrow is always on the emitter side. Okay, so wherever you see an arrow, it's your emitter. And the other one is the collector, and this is the base goes into this, the hat part, whatever you want to call it. Now, for some reason, don't ask me why, like this comes from, and I don't know why Spice did this, but usually bipolar devices their names start with Q. And if you're doing Spice, which is a simulation program, you always start the name of those things. You just have to start them with Q. So that's why it's Q1. So now, because we have three terminals, now remember in a diode, we just had two voltages, one voltage really we have to worry about because we had two terminals. So we just had VD, right? So we had VD versus ID. But in a bipolar transistor, because we have three terminals, we have three voltages. We have the base to emitter voltage. Okay, so in this circuit, this base to emitter voltage would look like, so this is base emitter. I'm gonna erase this here for now. Collector. So V1 would be in this thing would be the base emitter voltage. And the collector base voltage would be the difference between, so this would be this voltage, whatever this is. I'm not going to go on like that. Let's see if you just said, hey, this is, oops. You just said, this is the difference between these 2 points. Okay, the base collector voltage. And then the collector emitter voltage is from this output to the emitter. So in this case, sort of our collector emitter is, you can see it's the output, because eventually we're going to use it as such. In this case, it's like the output. We put a resistor here. This looks like our output. This base emitter looks like our input. That's where we're going to stick our input. And the collector base is strictly not connected, but we'll see that the value, as long as it's within a certain range, it's what's important, but not necessarily the exact value. Okay. Okay, so let's see how this works from, and I'm going to go through this pretty quickly because, again, it's like a rabbit hole. We could really go in this from a semiconductor physics standpoint in a big way. But let's just look at a PN junction, okay? So don't just think about it for a second. Don't think about an NPN, just remember the PN junction. And remember that we basically, because of the holes the diffusion current of holes leaving this area going to the N area, and the electrons leaving the electrons going in the hole area. We left stationary ions, positive ions on this side, and negative ions on this side. And then this created this electric field that points from the positive ion direction to the negative ion direction. So basically, this electric field is fighting the flow of electrons from here to here. Okay, so you guys are going to remember all this stuff, and it's exactly enough to stop that drift, the diffusion current from the N to the P. And the electric field also is stopping the flow of holes from the P side to the N side. It's exactly the right amount to stop that diffusion current. And so you're stopping current flow, okay? So now imagine that somehow magically we could inject electrons from the outside into this region, which also remember was called the depletion region. This was called the depletion region because it was because it was depleted of electrons and holes. Okay, so it was depleted. Now from the outside world, we're going to start sticking electrons here, throwing electrons in here somehow. Okay, now notice that since you put an electron here, the electric field is going to actually push this electron, so that it's going to be an electron happening here is the electric field is going to actually push him into this area. So as soon as we get an electron injected here, it's going to start generating a current of its own of these electrons going into the N side. Okay, if we could inject these things in there. Okay, and in fact, that's what happens when we have, let's just look at this. So if we, depending on how we connect this NPN, okay, let's, for the sake of discussion, let's say that we make this, let me just draw this without the current here.
Dog is quiet.
What's that?
Your dog has been quiet for a while now, until now.
It must be the people are, yeah, it just like really takes off at, between 4 and 5:30. I guess people are walking at that point. It's, I hate to mess with it, it's fun, But okay, so let's say we, for the sake of discussion now, let's say we connect this to ground and we put, positive here, voltage here of 0.8 volts. Okay, now let's just look at this PN junction now. Okay, if we just look at that, so if I just look at this, I'm hoping this won't confuse you guys. If I just look at that part, so the P is, so kind of like if I just look at that, it looks like the P is at 0.8 volts and the N is grounded. So this PN junction, or the base emitter junction, is forward biased. Okay, if I put 0.8 volts here and 0 on the emitter. Okay, now, if I have a choice for what to put for the collector, let's say I make the collector, in this case, 1 volt. Sorry, I'll make the collector, make the collector 1 volt. So the collector emitter voltage is 1 volt. Okay. Now let's look at this junction. This junction under that case. So it looks like PN. Sorry, these guys are jumping into each other. So this is 0.8 volts. And this is 1 volt. So if I was going to just draw this guy, it would look like the N side is at 1 volt and the P side is at 0.8 volts. Meaning that this junction is reverse biased. Okay, so if I draw it all up here again, so I made a base emitter voltage. So the base emitter, this is the base. So if I put 0.8 volts on the base and ground the emitter, and I make this 0.8 volts, so this junction is forward biased. Okay, and if I put a battery, 1 volt battery across the collector and the emitter, this is the reason this is connected to the grid. This emitter is grounded, so this is collector to emitter. Then this voltage, so the collector emitter is going to be 0.2 volts. Okay, so this becomes reverse biased, and this becomes forward biased. So these two junctions, that's what they're going to do. Okay, so basically we're going to have, if I look at, don't look at these arrows for the time being of volts and currents, but if I just look at, because this is reverse biased, you'll have a depletion region, like a physical depletion region around this area. Okay, so this is reverse bias again, and this is forward bias. Because this is forward bias, there's no depletion region there. But this guy's reverse bias, so we'll have this depletion region. Okay, so what happens? Now let's say this is let's say I inject a current of holes into the base from my input. Okay, so this current is going to go into the N plus. Okay, so if this is, remember, this is now forward biased. Okay, so when a junction is forward biased, you get your diffusion current back. Meaning that as soon as I forward bias this, the holes are going to again go into where there's few holes here, and the electrons are going to go where there's few electrons here. Okay, because this is again a forward. As soon as you're forward biased, your diffusion current starts, because there's no built-in electric field here to oppose that current flow. Any questions about that? This is just sort of the stuff that we covered on diodes. I know there's a lot of stuff going on here, but stop me if it gets confusing. But
Professor?
yeah.
Go ahead.
Oh, okay. So one side's forward biased, the other side's reverse biased.
Yeah.
Does that just kind of mean that it's switching on and off, like on one side and the other, so it kind of flips, like, or is it like
No,
how
I
exactly
think
does that work? Like when you're actually,
It's not doing any switching so far. We're just having DC voltages. So we have a constant voltage here, a constant voltage here, and a constant voltage here, which is 0. So at the moment, this is sort of continuously in reverse bias. This is continuously in forward bias, if you want to think of it in terms of time. But there's nothing changing with time. So nothing's like switching back and forth. We're just keeping it like that. Is that what you were asking? Jason?
I guess so. I mean, I think it's like because this is, what is it? I think previously you mentioned that it's like a diode, but like now it has like 2 sides, right?
Yeah.
not exactly though.
Is it?
Well, like,
I mean,
go ahead. Go ahead, Arthur.
I mean, from what I get here, it's supposed to act like 2 diodes are physically, but it doesn't really act like it. Is that correct?
Yeah, and I'll show you guys. It could at this point, like if this guy, if this P was very physically long, if this was like a large size, then it would just look like 2. If this was long, this distance between these two, then it would look like 2 separate diodes. It would look like you have one diode here and one diode here, or one PN junction here and one PN junction here, and they wouldn't talk to each other. But as we'll see in a bipolar transistor, we make this intentionally, we make this length very, very short. So basically this forward bias junction starts interacting with this reverse bias junction. And that gives us this functionality to make this look like a voltage controlled current source, okay? But for the time being, as I'm just talking about this right now, just this right now with this being forward bias and this being reverse bias, right now that's just the fact. It doesn't affect anything, right? Like it could just be 2 separated diode, and just because I have a voltage here, so I've made a careful choice of voltages to make this forward bias and this reverse bias. That's all I've done. And if we just sort of work out what happens if I put 0.8 volts here on the base to emitter and 1 volt from collector to emitter, it just looks like I have 0.2 volt reverse bias here across this PN junction, and sort of a 0.8 volt forward bias across this junction. Okay, so that's all we're saying at the moment. Okay.
Yeah, Professor, I have a question too.
Yeah. What's up, man?
Out of curiosity, with the length of P, that junction in between them, like you said, the size, would the size of that create like a different amplification constant? So like would we need like a higher VBE voltage in order to overcome that, like an electric field? Is that how like they design it?
Well, it's I think you're going in the right direction, but it won't be quite, well, to some extent it'll be a higher VBE, but as you'll see, if you make this length different, you'll give this a higher, you'll give it a higher current gain. But like you're gonna like, I think we'll need a couple more steps before you see how that works. But that is definitely an engineering, like definitely a big engineering tool, how wide you make that and what that does to the current. But it will, it'll increase the VBE that you need, because there's also some resistances here, et cetera. But it's definitely an engineering choice. Does that answer your question?
All right, yeah, that makes a lot of sense.
Okay. So in fact, so just to follow up with Melvin saying, one of the engineering choices, the two major engineering choices in bipolar transistors is this separation. And the second engineering choice is the choice of doping concentrations. Like what is the value of this N compared to this P compared to this N. Notice now, I mean, there's a lot of stuff here to notice, that this says N plus. Okay, in fact, let me see if we had that going on before. Nope, we didn't mention it here, but I guess here is the first time we're mentioning it. This is N plus. And what does N plus mean? N plus means that it's very highly doped N. Okay, it just means you've like really doped the hell out of it. So the number of donor or the donor concentration in this area is like very, very high compared to the acceptor. So the P basis is P. So this is like not very high doped. Na. So that means if I look at the, this emitters N sub D is much greater than basis N sub A. So that's another big design choice. And the reason for that, let me just mention it. Well, no, let's stop right there. Sorry guys, because it's like I think it's like hard to figure out a good stopping point here. I think I'll just sort of restate this and we come back on Thursday and sort of work our way through it. So anyway, I think that the main things I want you guys to take out of this today is this, just again, this concept that if we had a voltage controlled current source and like an external resistor, would be a way to get an amplifier. So that's one. Two, if we use a bipolar transistor and we put it in the right operating points, like we're about talking about, you will get a voltage controlled current source and it'll have this exponential relationship between the output current and the input voltage. Okay, so that's the second thing to remember. And then sort of that the bipolar transistor looks like these back-to-back diodes, one of which we're putting in reverse bias and the other one we're putting in forward bias. So just kind of, those are the main things from today, and then we'll follow on again on Thursday. Any other questions, guys? Okay, guys, if not, I'll see you guys on Thursday. Take care.
Thank you.
Professor,
Thank you.
Yeah.
I wanted to talk about my quiz submission.
Yeah.
So I know that I submitted it without like my name on the file, and I didn't see. Well, I saw your email on Saturday, but I sent it on Sunday. I wanted to know if you got it on Sunday or because let me check. I sent one today, but I didn't see that I had sent one on Sunday, even though I thought I did.
Yeah. I'm being passive aggressive towards you. This is called passive aggressiveness because I'm unhappy that you didn't submit it correctly.
No, yeah, I understand. Yeah.
So
No, that's my fault. That's not me.
Yeah. Anyway, so I'll grade it. I was just, this is my passive aggressive nature. So you're okay, but yeah, please make sure you submit it correctly. And I'm like trying to remind you guys of doing that. So anyway, appreciate it.
Okay. Well, I wanted to know if it went through, but okay. Thank you.
Sure.
Professor, I did like similar thing. So you mentioned that I didn't name the file, but I redo it and send it again, and I believe I put the name under my name, but I wasn't quite sure what did you mean.
Oh, okay, let me see what.
So you told me that I didn't put my name as the folder name.
Yeah, let me see, maybe I screwed up. Where are you? Yeah, you're right. I think I screwed that up. No, you had it right, boy.
I just wanna make sure because I don't wanna be having a problem and then submit it the same mistake Nick in the next one.
No, you had it right. And I saw that you sent me the problem too, so I'll grade that and include it in your grade.
Thank you.
Sure.
Thank you so much. Have a good one.
Okay, thanks. Bye, guys.